Sounds good.
Excellent. Things are good with you?
Things are fine,
Okay.
Obviously stuck at home and doing everything that one does from there. But thankfully nothing dramatic going on.
Right.
Are you at all involved with this new website where all these seminars are being compiled?
No, I only just jumped onto it last night to advertise yours. So I now have registered, and I put our groups series up there and your talk as well. So I think we're getting some people from that. It looks really great, by the way.
It's very impressive. Yeah, it's very impressive,
yeah.
and it's much more organized than what was before.
Yeah, so. Yeah. So I actually think, as I said when we did one of these a couple of weeks ago, I really think this is a positive outcome. Looking for positives where you can of this whole situation, because I think we're going to end up talking to each other more. I think more people will end up giving effectively more seminars at more places by virtue of this. Now everyone is used to the technology, which has been around for a while, but I think people have been reluctant to use it. But now we've been forced to use it. I think we'll continue to use it. Yeah. Okay. So let's see. I think we definitely have an audience, and so maybe I will get you started.
Sounds good.
Okay. So I'll just admit a few more people. And okay. So I just want to send one more message to one of my co-hosts, and then I'll get you started.
Co to je za výraz?
Okay. Okay, great. So yeah, I think we should start. So assuming that everyone can hear me. So welcome everyone to USC virtually. And today we have Thomas Dumitrescu, and he's going to tell us about, well, the title of the talk is An Introduction to Two-Group Global Symmetry. What we'll do is go for about an hour or so. If you have a burning question, feel free to unmute yourself and see if you can get his attention. But we'll mostly just carry on for the hour, and then I'll moderate a Q&A at the end for about 10 or 15 minutes. So hopefully that works. And feel free to private chat me as well if you prefer me to call on you for questions. But hopefully everything will go fine. Okay, so without further ado, Thomas, you're up.
All right, thanks, Cliff. Thanks, Cliff and Christoph, for inviting me to give this virtual talk at USC. It's nice to be at USC in this fashion. These guys asked me to talk about some recent work, but also to give a little bit of a pedagogical kind of introduction to some of the basic themes. So I will discuss a subject that I've been working on a little bit, goes under the general topic of two-group global symmetry, or higher group global symmetry in general. And the papers that I will mostly be talking about are these two papers with Clay Cordovine and Ken Trilligator. The second one hopefully to appear soon. And I do want to talk about some of these recent results, but I will also take the first 20 minutes or so to give a little bit of a rapid overview or introduction to higher form symmetries and some of the words that will appear later on. If that means that I run out of time to talk about some of the applications at the end, that's fine, or we can do some of that in the questions or offline. So we'll sort of see how it goes. So, you know, the subject of symmetry in quantum field theory is old and vast and nevertheless vibrant and constantly expanding. So let me start with something very simple and familiar, which is, you know, maybe the most basic example of a global symmetry in quantum field theory, which is just a U1 flavor symmetry. For example, you could imagine thinking about baryon number in the context of QCD. And Noether's theorem tells you that there's a conserved current, J mu, for this symmetry. And in order to set up the sort of notation I'll be using throughout the talk, I will call this standard U1 flavor symmetry an ordinary or a zero form global symmetry. And I've always tried to indicate form degrees by little superscripts. So when I put a superscript 0 in parentheses here, that's to remind me that I'm talking about a zero form global symmetry. At this point, that's just a name. And if I write the current in one form notation, then I'll put a little superscript 1 on it. So J superscript 1 is the one form current, and it satisfies standard conservation equation written like this. And this is an operator equation that's valid inside correlation functions as long as you don't collide with any other operators or insertions. And this conservation equation has the consequence that you can construct topological charge operators. For the moment, by the way, I'll be in 4 dimensions. I'll start the beginning of the talk in 4 dimensions. Eventually, we'll transition to 6 dimensions. So these topological charge operators are integrals of star J1 over 3 surfaces, 3 cycles. And because star J1 is a closed 3 form, those charge operators do not depend on small deformations of sigma 3. So that's the sense in which they are topological. These are the standard Noether charges associated with the current J. And what are the things that are charged under these standard currents and these standard symmetries? They're simply local operators. So for example, if you think in Euclidean signature in R4, you can insert a local operator O of X at some point, and then you can surround it by a 3-dimensional hypersurface sigma 3 that links the point X inside 4-dimensional space. And that configuration simply measures the charge of that operator under the U1 symmetry that we're talking about. So that's what this is supposed to signify. And so here I'm saying what the situation is for charged operators. Of course, you can act with O of X on the vacuum and create a state that is charged under the symmetry. And typically, O of X will create charged particles when you do that. Let's imagine you're in a phase in which you have sensible point particles. So the charged things under these familiar or ordinary or zero form global symmetries are local operators like O of X and charged particles. Okay. So there's one more layer of structure that I need to remind you of that will be important later on. Just like any other operator in quantum field theory, it's always good advice to couple your current J1 to a classical source, a non-dynamical background field. The background field will also be a 1 form or a vector. I'll call it big A1. And it'll be the standard coupling of a current to a background vector field. If I write that in form notation, it looks like this. And it's a standard fact that the conservation of the current as an operator equation is in direct correspondence with the statement that the partition function or the generating function of the quantum field theory that we're talking about in the presence of this background field A1 is invariant under gauge transformations of the background field. These are background gauge transformations. They're standard looking gauge transformations where you shift the 1 form A1 by d of a 0 form gauge parameter lambda, modulo the fact that lambda might not be completely globally well defined. So these are conventional U1 background gauge transformations, and A1 is a conventional U1 connection. So this is the sort of rapid summary of a very standard story. And the thing I want to remind you of next, or tell you about next, if you haven't heard about it in detail before, is that this set of words that I reviewed for you has been generalized in a variety of important ways. And two of the kind of key papers crystallizing that are listed here. And this generalization goes under the name of higher form or generalized global symmetries. So the simplest example of such a generalization, and the main example that I'll be talking about, is to upgrade from a standard or zero form symmetry to what's called a one form global symmetry. And I'll discuss kind of the analog of a U1 symmetry in this higher form context. So I'll call this U1 superscript 1. So what changes when I upgrade from a zero form symmetry to a one form symmetry? For example, instead of having an ordinary current that is a one form or a vector field, the current is now a two form. So big J2 is going to be the two form operator that will serve as the conserved current of this one form global symmetry. And it still satisfies a standard conservation law of the same sort that an ordinary current does. And that looks like this. So D star J2 is still 0. If you write that out in components, then J is a two-index antisymmetric tensor, and its conservation equation is a standard-looking conservation equation like this. So we can repeat everything that we said before. For example, the conservation of J enables us to define topological operators, topological charge operators. And because star J2 is now a closed two form rather than a closed three form, the appropriate cycle to integrate it over is a two cycle. So in 4 dimensions, these topological charge defects are now supported on 2 cycles sigma 2, like this. And the fact that the charges now live on 2 cycles rather than 3 cycles mean that the objects that they can link are also of a different dimension than in the previous case. And so we have to figure out what the dimension is. What dimension can a closed 2 cycle link in 4 dimensions? Well, in 4 dimensions, those would be lines or curves. So to set this up in the most intuitive way, imagine that you were thinking about 4-dimensional spacetime, which I'm drawing here in a 3-dimensional projection, and you imagine inserting some kind of line defect. Maybe keep a Wilson line in the back of your mind. We'll discuss it shortly. But really any kind of line defect, and just insert it along time. So this is like a probe particle sitting at a point in space and moving along time. And P here is some event along that particle's world line. And if you slice this picture in constant time, what you get is 3-dimensional Euclidean space drawn over here, where P is simply a point. And a point in 3-dimensional Euclidean space is linked nicely by a two-sphere or lots of other compact two surfaces. So what we need is sort of the upgrade of this picture to 4-dimensional spacetime, and that adds one additional dimension, which is the time dimension, and turns P into its world line. So this is why a 2-cycle in 4 dimensions links a line defect. By contrast, before we had a 3-cycle that linked the local operator. So what that means is that using the same logic as before, the objects that are charged under these topological surface operators, these topological surface operators are now line defects. Or if you orient them in a kind of different way, they can be viewed as line operators. And just like local operators can create point particles, line operators or line defects can create dynamical string states if you're in a suitable phase of the theory. So by far the simplest example of such a one-form global symmetry occurs in free Maxwell theory in 4 dimensions. And it occurs with sort of a double force because you actually get not 1, but 2 independent one-form global symmetries. So free Maxwell theory is a free abelian gauge theory in 4 dimensions. It's built on a dynamical gauge field little a. Little a is a dynamical variable. It's integrated over in the path integral. And little f is field strength. And the equations of motion and the Bianchi identity tell you that both f and star f are closed 2 forms. So free Maxwell theory supplies you immediately with two closed two forms. And we just said that closed two forms, or more precisely their stars, are conserved currents for one-form symmetry. So we get two different one-form symmetries. We'll call them electric and magnetic. The electric one corresponds to picking the current to be F itself, or proportional to F itself. And then the rule we said above tells you that these topological surface operators are just the integrals of the star of F over a two-cycle. And the integral of the star of F over a two-cycle is just the integral of the normal electric field over the surface sigma 2. So this surface sigma 2 is like a Gaussian surface, and this integral over E perp computes for you the electric charge inside sigma 2. So this is why this is called the electric one-form symmetry. The magnetic one-form symmetry is exactly the same, except with F replaced by star F. So when we define our topological surface operators, we integrate F over the two-cycle sigma 2, and that translates into the integral over the normal magnetic field over sigma 2, and that's a Gaussian surface integral that measures the total magnetic charge inside my surface sigma 2. So what we learn from this is that these charges simply measure electric and magnetic charge, and by immediate deduction, that means that the charged operators are electric and magnetic line defects or line operators. So these are very familiar, especially the electrically charged ones. The electrically charged ones are simply the Wilson lines of the theory. So these are line defects that represent world lines of infinitely massive or non-dynamical electric probe particles. And so here I've drawn such a particle propagating a long time and sitting at a fixed point in space, and the world line of this particle will be denoted by C. So we can simply construct Wilson lines in this simple abelian theory by integrating the Maxwell gauge field along C and exponentiating it with an integer coefficient Q, which tells you the electric charge of the line that you're talking about. And if we apply our Gaussian surface operators in this context, in other words, if we place such a topological surface operator on a two-sphere linking this line, then that simply measures the electric charge of the line. Okay, so that's easy. The kind of slightly less trivial charged operators are the ones that are charged under the magnetic one-form symmetry. These are the infamous 't Hooft lines. So these are line defects that represent the world lines of infinitely massive magnetic probe charges. And the picture is exactly the same. We have the world line of these probe charges and we link it by sigma 2. But now, in order to define the 't Hooft defect, we need to work a little harder. So these cannot be defined as local insertions into the path integral. They need to be, at least in the frame that we're using, they need to be defined as disorder operators by putting singular Dirac monopole boundary conditions on the line C. And once you do that, then you can insert your magnetic surface operator here and read off what the magnetic charge of the 't Hooft line is. Okay, so that's a lightning review of electric and magnetic one-form symmetries in Maxwell theory and the corresponding charged operators. And remember, I said that we would need a kind of final step in this discussion to get us where we want to go, which is we want to couple all interesting currents to suitable background gauge fields. And in the context of ordinary symmetries, those were simply background one-form gauge fields of ordinary Maxwell or Yang-Mills type. Now we have conserved currents JE and JM that are two forms, and therefore the appropriate background fields will also be two forms. And so what we are supplied with then is a situation in which we're kind of naturally led to turn on two-form B fields, and in this case we have two of them, B electric and B magnetic, that couple to these currents. So these are B fields exactly of the type that one encounters in supergravity or in string theory, except that they are not dynamical. They don't satisfy equations of motion. They're not integrated over in the path integral. Instead, they serve as classical sources in the partition function, or alternatively, they define the generating function for these operators. So here's the coupling. We couple them exactly like we coupled the ordinary gauge field before. And when we write those couplings out in terms of the Maxwell field F, the dynamical Maxwell field F of our theory, we recognize that at least one of these terms, the magnetic term, looks like a totally standard BF coupling in 4 dimensions, where F is dynamical and B is a background field. And the electric one looks like a slightly less standard BF coupling because it has the Hodge star here. So roughly speaking, it's kind of a, I don't know, I could call it an electric BF coupling or something like that. And the statement that the two-form currents, the electric and magnetic two-form currents, are conserved, again translates into the statement that your partition function in the presence of B electric and B magnetic is invariant under background gauge transformations of these B fields. And because they're B fields, those gauge transformations are of the standard type where the gauge parameter is itself a 1 form. Okay. So this is, here I'm suppressing many details, and I could say much more. For example, I'm totally ignoring the possibility of interesting 't Hooft anomalies that appear in these background gauge transformations, which do actually exist in this example. We'll have plenty of opportunities to mention anomalies later. So this is sort of the beginning of a rich and beautiful story with many recent papers and results going off in different directions. And the sort of basic point that you should keep in mind is that symmetry is good. The more symmetry you have, the more you can say about a quantum field theory. That's especially true if your quantum field theory is strongly coupled and you don't otherwise have that many knobs to turn. And so more symmetry is better. And this whole story about one-form symmetries and higher form symmetries generalizes to interacting theories with matter and to non-abelian gauge theories. And there are discrete versions of these symmetries that play a role there, and they can have anomalies, and you can do anomaly matching, and sort of many of the nice things that you expect in the context of having a global symmetry still make sense, and that leads to the usual kind of consequences like handles on interesting gauge dynamics or checks of dualities. So so that's sort of not the route that I'm going to go down. Instead, I'm going to tell you about kind of a further generalization of global symmetry that sort of goes one step beyond what I reviewed for you so far. And the direction which I want to go is the following. So broadly speaking, in many examples, the ordinary zero form symmetries and these generalized higher form symmetries sort of live in different universes. They don't really talk to each other. They're somewhat decoupled. You have the local operators and they're acted on by zero form symmetries, and then you have the line operators and they're acted on by the one form symmetries. And, very crudely speaking, these things sort of are, somewhat independent. Of course, when you look at the details, that's no longer the case. But what I want to do in the rest of the talk is show you a couple of examples where they really don't decouple at all, where they really interplay in a kind of very dramatic and intimate and rich way. So where they cannot be sort of thought about separately, even in principle. And I could try to explain the subject in a variety of ways. If I had more time, for example, I might give you a list of simple toy models in 4 dimensions that we spent some time analyzing in the first paper that I mentioned. But then I wouldn't have any time to say anything about 6D and about more recent stuff. And since this is a string theory seminar, I feel like it's a good idea to talk about 6D. So what I'm going to do is jump directly to 6 dimensions for the rest of the talk and give you the appropriate generalization of global symmetry in that context, and then hopefully mention some applications. If there are questions about 4D or about what the analog in 4D is, then we can discuss that after the talk. So why do we care about 6 dimensions? Well, possibly for lots of reasons, but an important reason is string theory. So string theory has supplied us and keeps supplying us with very interesting examples of, here I wrote SCFTs in more than 4 dimensions, but I should say many different kinds of non-gravitational theories in more than 4 dimensions. And as I said, I'll only discuss 6-dimensional theories in this talk. And by taking decoupling limits of string theories or various brane constructions within string theory, people have constructed lots of different UV-complete theories without gravity in 6 dimensions. And in general, if you do such a decoupling, what you'll end up with is not a local quantum field theory. So it's generic decoupling limits lead to little string theories, which are characterized by a little string mass scale, MS. But sometimes you do get quantum field theories out in the end, as I'll review on the next slide. And so far, nothing I've talked about has involved supersymmetry, but from now on, all the interesting examples that I'll discuss will be supersymmetric because all of the known reliable constructions of the kind I just mentioned are themselves supersymmetric. So for the rest of the talk, I'll mostly discuss 1,0 or 2,0 or 1,1 theories of different kinds in 6 dimensions. Okay, so what happens if you look at these little string theories at low energies in the deep infrared? So if you look at energies below the little string scale, far below the little string scale, then you will flow to a low energy effective quantum field theory description, typically deformed by a bunch of irrelevant operators. And in general, that's just an effective description with a cutoff. And you really need the whole little string theory to make sense of the UV. So roughly speaking, there's a bifurcation of scenarios here, which I want to remind you of. The one route, which I guess I labeled 2 here, is that you flow to a weakly coupled infrared-free quantum field theory at low energies, which is in general not conformal. And you can typically write a Lagrangian, a supersymmetric Lagrangian for these effective field theories. And they're not UV complete. They're sort of what you would expect in this kind of situation, an effective field theory with a cutoff, roughly speaking, given by the little string scale. In other cases, you flow to the deep IR and you find that the theory in the deep IR is actually a conformal fixed point. In fact, a superconformal fixed point, because we start with a supersymmetric theory to begin with. And these are very interesting, and they're generally strongly coupled and generally don't know how to formulate a Lagrangian for them. And then if you have such a situation where you land on a superconformal fixed point, you might imagine studying that conformal fixed point on its own, since it is by itself UV complete. So you can decouple it from the little string theory in which it was embedded. So having said all of that, I will be discussing both scenarios in a little bit of detail, but I will mostly view each of the 2 sides as giving me interesting low energy quantum field theories. And the question of UV completion will mostly take a backseat to what I'm saying, but I wanted to set it up this way just so you have it in the back of your mind, what kind of universe of questions this discussion lives in. So as I said, we'll sort of explore both classes of theories. And as you might have imagined, given the first part of the talk, we will focus on the global symmetries of these theories. And as you'll see in a little bit, also their anomalies, which is always a closely related subject. When you're discussing global symmetry, you should also look at any anomalies. And one feature of the theories on the previous slide, of the 2 different classes of theories on the previous slides, so this class and this class, that sort of unites them and at least gives them a common thread, is that both of these types of theories typically have non-abelian gauge fields of Yang-Mills type that reside in vector multiplets of supersymmetry. And that's true both for the superconformal theories and for the infrared-free non-conformal theories that you get from other little string theories. And in 6 dimensions, the Yang-Mills gauge coupling, if you do dimensional analysis, has units of length squared, or 1 over mass squared, where this cutoff lambda in the cases that I mentioned before is really something like the little string scale. And so the Yang-Mills gauge coupling is irrelevant in 6 dimensions. So a Yang-Mills theory by itself is not really ever conformal in 6 dimensions. And therefore, these little string theories that just flow to infrared free Yang-Mills theories and nothing else are really not conformal in the IR. For superconformal theories, it's a little bit more interesting because the Yang-Mills fields, when they arise, always live on the tensor branch of the superconformal theory. That's the branch of the moduli space of vacua that's parametrized by scalars that reside in tensor multiplets. And that's the direct 6D analog of what in 4 dimensions with 8 supercharges you would call the Coulomb branch. And it turns out that the other fields that are present on the tensor branch can couple to the Yang-Mills fields in such a way as to fix up the fact that they're not by themselves conformally invariant. So I said that the vast majority of these theories contain Yang-Mills fields. If you think back to maybe your top 2 examples of interesting SCFTs in 6 dimensions, you might complain because they don't actually have vector multiplets. So for example, the 2-0 theory doesn't have vector multiplets on its tensor branch. If you talk about it in 1-0 language, it only contains tensors and hypermultiplets. And the theory of small E8 instantons in 6 dimensions has an even simpler tensor branch, which is described by a single tensor multiplet with no additional light fields. So these are very interesting, and you know, they're some of the first examples we encounter when we learn about the subject, but they're a little bit non-generic in this sense. The vast majority of other examples that we know about do have vector multiplets that couple to the tensors. Very good. So why am I harping on about Yang-Mills fields in 6 dimensions? And the reason is that in 6 dimensions, all Yang-Mills gauge theories are automatically supplied with an interesting operator. And that operator, which I'll call J2 with a subscript I for instanton, is the Hodge star of what in 4 dimensions would just be the instanton density. So the second Chern class of the non-abelian gauge field of the Yang-Mills theory that you're talking about, this is roughly speaking trace F wedge F, and it's a 4 form in 6 dimensions, so its Hodge star is a 2 form, and that's my J sub I 2 form. So this is the instanton 2 form, and because the second Chern class is a closed 4 form, the instanton 2 form is actually a conserved 2 form current. So it satisfies this conservation equation for a 2 form current, which we've already encountered in our basic discussion of 1 form global symmetries. So what that means is that whenever you have a non-abelian gauge theory in 6 dimensions, it automatically comes equipped with an interesting 1 form global symmetry, so called the instanton 1 form symmetry, U1 sub I, that is defined by this current. Okay, so just like Maxwell theory in 4 dimensions automatically came with 2 interesting 1 form symmetries, any non-abelian gauge theory in 6 dimensions comes with this interesting 1 form symmetry. And we said that the charged objects under such a 1 form symmetry are generally line operators, line defects, or strings. And we can actually say explicitly what they are in this 6-dimensional context. In 6 dimensions, if you want to link a string, you should integrate your current over a 4 cycle. And indeed, the instanton density in 6 dimensions is a 4 form, so you can integrate it over a closed 4 cycle sigma 4 to get an integer, and that integer is the instanton number. And the instanton number in this context counts the instanton charge of strings or line defects linking that 4 cycle. Very good. And the last step to complete the program that I set up in the beginning is to take this interesting two-form current and to couple it to a background B field, a non-dynamical B field. And if you write that out in terms of the instanton density, then you get something that again looks like a standard DF coupling, standard Green-Schwarz coupling, you might say, where the B field is again a background field and the dynamical part here is constructed out of the, in this case, non-abelian Yang-Mills fields. Okay. Okay, so let me discuss my sort of simplest example. There are many examples. They're all kind of similar. Let me discuss this one because the theory involved is so familiar. This is the little string theory with 1,1 supersymmetry that you can get, for example, by decoupling gravity in type 2B string theory with a stack of NS5 grains. And this is a system, this is a half BPS configuration, and you'll end up with a theory on the branes that has 1,1 supersymmetry, which from the point of view of field theory is maximal supersymmetry in 6 dimensions. Okay, it's the analog of n=4 supersymmetry in 4 dimensions. And supersymmetry in 6 dimensions is chiral, so you have in general left-handed and right-handed supercharges, and here you have one of each in this 1,1 context. And you have an associated R symmetry, which acts on each supercharge. So you have an SU2 that acts on the left supercharge and an SU2 that acts on the right supercharge. And together they make an SO4, which you can think of as transverse rotations to the brane stack. And if you flow to the deep infrared, then this little string theory flows to the unique non-gravitational theory with 16 supercharges, which is 6D maximally supersymmetric Yang-Mills theory. And if you just start with a stack of NS5s, you get a non-abelian gauge theory with gauge group UN. So we can do the usual thing and decouple the center of mass and forget about the U1 for what I'm going to say in the rest of the talk, and just focus on the SUN part. So this has, like all other non-abelian gauge theories that I was talking about, this instanton one-form symmetry. And in this case, the instantons have a very beautiful interpretation because they're simply the F strings of the underlying type 2B theory, or after decoupling, they're the little strings in 6D. And similarly, the background field that you couple to the instanton number is the NS&SD field, or whatever is left of it after decoupling. So why is this interesting from the point of view that I would like to discuss today? It's a beautiful story, of course, but what do I want to say about it? Well, what I want to talk about next is the anomaly structure of this theory. It's also a very classic subject, was analyzed in the 90s. And in 6 dimensions, the standard perturbative anomalies are summarized by an 8-form anomaly polynomial that's constructed out of various characteristic classes. And in this particular case, it's easy to calculate the anomalies from the super Yang-Mills description. And in general, this I8 anomaly polynomial can have 3 different kinds of terms. And they'll all be interesting from the point of view of what we'll have to say. So I'll call them I8 gauge, I8 global, and I8 mixed. I8 gauge, which I'll discuss first, is what you usually think of as a gauge anomaly. In other words, it can only contain characteristic classes of the dynamical SUN gauge field. This could be an irreducible C4 or reducible C2 squared anomaly, but it involves the dynamical gauge fields. So if you think about it in terms of diagrams, then these anomalies come from box diagrams. Remember, boxes are the analogs of triangles in 6 dimensions. These come from box diagrams that have dynamical SUN gluons on every external leg. And if one of these diagrams or one of these anomalies is non-zero, the theory is simply anomalous. It simply has a gauge anomaly. It doesn't make sense even as a low energy effective field theory, let alone as a UV complete theory that comes from string theory. So all of these pure gauge anomalies must cancel for this to even be a consistent theory. And one small comment here is that because the theory we're discussing has no tensor multiplets that could potentially absorb some anomalies using some kind of Green-Schwarz mechanism, both the reducible and the irreducible anomalies have to cancel. So the whole I gauge has to vanish on the nodes. And in fact, it does. It's easy to check that it does. I think this I8 was worked out maybe by John Schwartz for the first time. I don't remember. I'm sorry, I didn't put the reference. So let's look at what's left. So I8 gauge vanishes. So we have two more pieces to look at. There's what I call I8 global, and there is I8 mixed. And let me discuss them in that order, because I8 mixed will be the most confusing one from the point of view that I'm going to describe. So I8 global is a piece in the anomaly polynomial that only involves background fields, no dynamical fields at all. So the exact opposite of the gauge anomaly we just discussed. It's a polynomial in the Chern classes of background fields for the SU2 left symmetry, the SU2 right symmetry. I have a Pontryagin class here, which characterizes the tangent bundle. So these are only background fields, and these anomalies are what are now commonly known as the 't Hooft anomalies for global symmetries. Right? These are anomalies that come from diagrams that look like these squares, but instead of having dynamical gluons on the external legs, you only have global symmetry currents. So for example, these C2 squared type anomalies for the R symmetry come from diagrams that only have R symmetry currents in the vertices. And these cross terms here between a R symmetry Chern class and the Pontryagin class for the tangent bundle characterize a mixed anomaly between the R symmetry and gravity. So they come from box diagrams that have two R currents and two stress tensors in the vertices. Okay. So these are very interesting. And again, they're the analog of triangle diagrams in 4 dimensions that have only global symmetry currents on the external legs. They're very interesting. But these 't Hooft anomalies do not break the global symmetries characterized by these currents. Right? These currents remain conserved as operators. They continue to satisfy their conservation laws at separated points. As long as you check current conservation at separated points, there's no problem. So the symmetry is not destroyed by the presence of these so-called anomalies. They do show up as interesting kind of C-number contact terms that violate naive ward identities at coincident points. So when various currents sit on top of each other, you can have certain contact terms and some ward identities that tell you about these anomalies. Maybe a more familiar way of saying the same thing is that if you turn on background gauge fields the way I was always doing before, and you look at the generating function in the presence of these background fields. So here we have the SU2 left and right symmetries, and we have background gravity. Remember, we said that current conservation was the statement that the generating function was invariant under background gauge transformations. So here I'm doing a background gauge transformation, both for the Yang-Mills field and for gravity. And the naive statement of current conservation is that the generating function should be dead invariant. If you have an 't Hooft anomaly, this is violated by a term that looks like a pure phase, and that includes the gauge parameters of the background fields that you're doing the gauge transformation to. And then these gauge parameters are multiplied by some C number expressions that I've not written out here. They're just C number expressions in the background fields. So that's why this is a very kind of innocuous, though interesting and important, but very, very innocuous violation of background gauge invariance. It's very controlled, that you can make absolute perfect sense of it. And it's the beginning of a rich and beautiful story, also a very well-known story. So let me sort of move on from that, because at least at our present level of understanding, we think we understand what these 't Hooft anomalies mean. And certainly they don't mean that the symmetries are gone. So what I would like to move on next is the last term in this anomaly 8 form, the one that I called I mixed. It's called I mixed because it contains both background gauge fields. So you have Chern classes for the SU2 left and SU2 right background gauge fields. And it's wedged together with a Chern class for the dynamic SUN gauge field. Okay. So this is a term that's half background and half dynamical. And translating the box diagrams from above, you see that you have a diagram that looks like this with two currents for the left or right R symmetries and two gluons, dynamical gluons, because of the two Fs that appear in trace F wedge F or C2. Okay, so this is a smack in the middle between the previous two cases. It's half gauge and half global. And remember, we said about the gauge anomaly with all gluons, we said that's a disaster. That breaks gauge invariance and we have to set it to 0. And with the 't Hooft anomaly that had only global symmetries, we said that's perfectly fine. It's very interesting, but it's perfectly fine. There's no problem with either gauge invariance or the global symmetry. So what's the deal with this diagram? Is it a problem for gauge invariance, like the all gluon diagram? Does it do anything interesting? What happens? Well, the fact of the matter is that you can regulate this diagram in a way that is completely consistent with gauge invariance. So roughly speaking, you can push the anomaly around in this diagram using sort of some more or less standard counter-term type arguments or choosing different regulators or momentum routings when you compute the box diagram. And depending on how you do that, you might discover that there's an anomaly in gauge symmetry on the gluon side, or there's an anomaly on the global side. And of course, you have to insist that gauge invariance is sacred. So you push the anomaly away from the gluons, making them perfectly fine. And then what you find is that something interesting happens on the global piece, on the global side. Okay, so what is that thing that you are left with once you insist on gauge invariance for the dynamical gluons? You learn that the global symmetry currents, J left and J right, satisfy an interesting, it's usually in this business called an interesting non-conservation equation. So its divergence in the presence of a background field looks like this. There's a number, n, which is the anomaly coefficient that appeared somewhere up here in my anomaly polynomial. Oops, where was it? Here it is. That's this number n, and you see it appears with one sign for the left currents and with the other sign for the right currents. That's why there's this plus minus n. And then on the right-hand side, there's an interesting 6 form. First, we have a 2 form, which is roughly speaking the field strength of the C number background fields for the SU2 left or SU2 right symmetry. It's actually literally dA, and it's not quite the field strength, but it's close enough. And then we have the operator that before we called the instanton current. So we have the 4-form instanton density, right? And the divergence of this current is a 6 form. So that's a nice equation to write. The right-hand side is supposed to be 6 form. And just like the box diagram was mixed between global and gauge symmetries, the right-hand side of this non-conservation has a piece that's dynamical, involves the gluons, and the piece that's just a C number background field. And this is the kind of non-conservation equations that we have kind of previously analyzed at some length in the context of simple 4D toy models with U1 gauge symmetry. That was the first paper I mentioned in the beginning. Here we see exactly the same thing happening in the much more rich context of non-abelian gauge theory in 6 dimensions. Okay, so what is the consequence of this interesting equation? What should we make of it? Well, one important consequence is that even though the right-hand side contains an interesting operator, the current J left and the current J right are still conserved. Why is that? Because when you do quantum field theory in flat space and you turn off all the background fields and you just ask questions about correlation functions of operators where none of the operators collide, then you're perfectly entitled to simply set this background field here to 0. And that means that the right-hand side of this non-conservation equation simply vanishes, and these currents are still conserved operators. Okay? So the symmetry is not gone. There's no destruction of the symmetry. For example, this is not what happens in the context of the U1 axial symmetry in QCD. In the context of the U1 axial symmetry in QCD, you get a non-conservation equation whose right-hand side is simply a non-zero operator, regardless of whether or not you have any background field turned on. And then the symmetry is simply destroyed. Here, that's not the case. Symmetry is perfectly good at separated points when the background field is 0. However, the presence of this background field factor means that there can be interesting phenomena when two operators collide. And that's exactly what happens. What happens in this model is that when two J left currents collide, or when two J right currents collide, then this equation tells you that their current algebra is deformed from the usual Lie algebra current algebra of a standard global symmetry to what we call a two-group global symmetry. And what this current algebra deformation amounts to is the statement that two J left currents can fuse into the instanton to form J2, and similarly for two J right currents. And they can do so with very particular coefficients, plus and minus n, that are dictated by the coefficients in this non-conservation equation. So there's a variety of intuitive ways of thinking about this fusion, but one that I like is you just look at this diagram. Right, this diagram has two J left currents coming in or two J right currents coming in, and it has two gluons coming out, and those two gluons can be created by the operator C2 of F, by the instanton operator, because the instanton operator has two field strengths in it, so it can create a two gluon state when acting on the vacuum. So this mixed anomaly diagram actually characterizes this deformation of the current algebra into what we call the two-group current algebra or two-group symmetry. So this characterization might not be particularly intuitive, and maybe you don't find it appealing. A much more recognizable version of the same story comes about when you couple all conserved currents to suitable background gauge fields, right? We've been following this mantra of coupling every current inside to a suitable background gauge field. And we'll do the same thing here. So we'll add a background gauge field for the left R symmetry current, we'll add one for the right R symmetry current, and we'll add a B field for the instanton one-form current, sorry, two-form current. So this is the current that couples to the instanton density. And if we just parrot everything that we did before naively, we would say that current conservation implies invariance under standard zero-form gauge transformations of these A fields, and current conservation of the instanton current would mean invariance under background one-form gauge transformations for the B field. This modification of current algebra in the presence of two-group symmetry means that these blue conservation equations, sorry, these blue gauge transformations that I've written here are no longer consistent. They're no longer tenable. These fusion channels force you to add extra terms in the transformation rule of the B field. And these terms look very familiar. So for example, in this context, the term that you would have to add is a term that involves the left zero-form gauge parameter and the field strength of the left gauge field, and similarly for the SU2 right as well, with their respective anomaly coefficients. So the two-group fusion rule adds extra terms to the transformation rule of the B field, and these terms look exactly like the terms you encounter in the conventional Green-Schwarz mechanism in string theory and in other contexts. The only thing that's new here is that the Green-Schwarz mechanism arises not for a dynamical B field, and the quote-unquote anomaly that it's canceling is not a gauge anomaly, but instead you have a background B field, it's not dynamical, and you're forced to introduce these Green-Schwarz transformations in order to capture a particular aspect of the current algebra of the currents that these background fields couple to. So the fact that this two-group symmetry structure has a direct analogy with the Green-Schwarz mechanism was, I think, emphasized early on by Anton Kapustin. And just like the Green-Schwarz mechanism is designed to cancel something that you don't like, in the original context, it was a gauge anomaly. These extra terms in the B-field transformation also cancel something that is kind of unpalatable. And the thing they cancel is the following. If you do the naive background gauge transformations of the A and B fields without the Green-Schwarz shifts, and you plug them into this coupling, and you use the conservation equations for the 1 and 2 form currents, and in particular, you use this non-conservation equation, which holds in the presence of the background fields, then you'll find that there's a piece involving the operator C2 of the dynamical gauge field that doesn't go away. So when you plug in the naive background gauge transformations, this coupling shifts by something that involves both background fields and the operator C2 of the dynamical gauge fields, which is exactly this star of the instanton 2 form current. And then you realize that you can fix this problem by making use of the fact that you already have this coupling, as long as you shift the B field by some additional amounts that you have to carefully fine tune to get rid of the unpalatable terms. Okay, so the logic is similar, but the words are different. Very good. So since I'm rapidly sort of approaching the end of my word line here, let me sort of try to wrap up what we said. The basic message of what I told you in the last half hour or so is that mixed anomalies between gauge and global symmetries that are, roughly speaking, of this type, where you have neither too many gluons nor too many global symmetries, lead to a somewhat new phenomenon. They lead to a deformation of the global symmetries in your problem to what we call the 2 group. And here the 2 group is just a statement that you have this mixing between the 1 form symmetries and the 0 form symmetries. Or alternatively, equivalently, you can say it by specifying that the B field necessarily has a Green-Schwarz shift. So I've analyzed for you just one example here. This was the 1,1 maximally supersymmetric Yang-Mills theory in 6 dimensions. There are many, many other examples. And in 6 dimensions, you can go through long lists of little string theories and you find very similar and interesting stories. You have little string theories with 1,0 supersymmetry where things are even richer. And there are perfect analogies to what I was talking about here. And once you realize that, and once you understand what you have to do in order to characterize this 2 group symmetry, of course, now you can start learning something because now you have a different symmetry structure than what you're used to, and you can start studying its implications. So you can start asking, for example, what are the anomalies with respect to this 2 group symmetry? Are they the same or are they different than the conventional 't Hooft anomalies you would find in the presence of 0 and 1 form symmetries? The answer is no. You have to reanalyze those, and there's some modifications. So this is if you wish, is the starting point for using the modified global symmetry to analyze theories that you care about. So I'm nearly out of time, but and I have said nothing about superconformal theory so far, but I want to maybe make a brief sketch of what any of this has to do with superconformal field theories in 6 dimensions. Well, it turns out that in 0th order approximation, there is nothing interesting to say because you can prove that 6D superconformal field theories cannot possibly have an operator like this 2 form current J2. Everything I said today was predicated on the existence of such a J2. The J2 is what gives you a 1 form symmetry, and the whole 2 group story involves a fusion between 1 form symmetries and ordinary global symmetries. So if you don't have the 1 form symmetry, to begin with, there's a fortiori no 2 group symmetry, and perhaps that's the end of the line. By the way, I should say that the way that one proves this theorem is one asks whether the operator J2, which is a very special operator, it's an operator of exactly dimension 4 It has to satisfy a certain conservation law because it's a conserved current. So it's a short representation of the conformal symmetry. One asks whether this short representation of the conformal group can be sensibly embedded into any representation of the superconformal symmetry that exists in 1,0 and 2,0 theories. And the answer is no. That's a problem that one can analyze exhaustively. We did that a number of years ago, and you can make lists of all the allowed currents that exist in supersymmetric theories, and J2 is not one of them. So superconformal symmetry plus unitarity rule out the existence of such a thing. Now, perhaps surprisingly, the absence of this current and the absence of two-group symmetry as a result actually has interesting consequences for the structure of superconformal theories in 6 dimensions. And the reason is the statement that I made at the beginning of this slide, which is roughly speaking that two-group symmetry, at least in the context that I explained it, comes about when you have interesting kind of mixed gauge global anomalies in quantum field theory. And in the 6D context that we were discussing, they were anomalies that involved 2 gauge legs and 2 global legs of a box diagram. So if you don't have any 2-group global symmetries in your theory to begin with, which is what this theorem tells you has to be true on a priori grounds, then it means that all mixed anomalies of this kind have to cancel. That's a very strong and surprising condition. It's not a condition that you would have ordinarily imposed on a garden variety quantum field theory. If I had asked you to list all the consequences of anomaly cancellation and gauge anomaly cancellation and so forth, you would not have included this condition. Because as I said before, these mixed anomalies don't do anything bad. They don't violate gauge invariance and they don't violate the global symmetry. And in fact, we saw that there are non-superconformal theories like the little string theories where these anomalies arise. So there can't be anything intrinsically bad about them. And instead, what we see here is that it's a special property of superconformal theories in 6 dimensions that these anomalies have to vanish. And once you understand that, of course, you can use it to study what that tells you about the theories that you're interested in. So for example, these authors, Omori, Shimizu, and Tachikawa, used this condition to compute the 't Hooft anomalies for the global symmetries in many 1,0 superconformal field theories. And for them, imposing this vanishing condition, even though it came kind of out of thin air, was an important assumption to get the answers that they could then check were right in many contexts. So if you now complete the cycle and you understand why this vanishing condition is true, you can compute many 't Hooft anomalies, and you can even prove other theorems about anomalies in 6D theories that you might care about. For example, one interesting anomaly that we often care about in the context of conformal field theories is the A-type anomaly. The A-type anomaly is a kind of Weil anomaly or conformal anomaly that appears in the A theorem in even dimensions. And it's been conjectured that this anomaly is positive in all interesting unitary theories. And in lower dimensions, like in 2 and in 4 dimensions, we have proofs of this fact. In 6 dimensions, we do not have a general proof that the A-type Weil anomaly has to be positive. But in fact, using this interesting vanishing condition plus a whole machinery of superconformal anomaly matching techniques, we can show that the A-type Weil anomaly has to be positive, at least in superconformal theories. Okay, so since I'm out of time, I'll stop here and I'll answer questions.
Thank you. That was quite wonderful. I hope we have yes, we have a good amount of time. So how to run the question session? We have about 60 people. I don't know how many questions. If people want to unmute themselves and just jump in with a question, we'll try it that way. If it becomes less than orderly, then I'll ask you to simply indicate that you want to ask a question on the chat, and then I'll take you one at a time. So let's see how it goes and just improvise as we go. So who wants to ask a question?
I had a question. If I understood the theory you're talking about, Thomas, in the case of a UN gauge group, the one form symmetry you were talking about was not the one that one would associate to the center of the gauge group, right? There's also there's also that one form symmetry. Does that play an interesting role here, or not really? For
that plays that. So that is actually that's the abelian U1 inside UN that you're talking about, and it played no role in what I was talking about. I was talking about the instanton symmetry of the non-abelian part. Now, an abelian gauge field in 6 dimensions it has both a one-form symmetry and it also has a three-form symmetry, because now F and star F are 2 forms and 4 forms respectively. So there's an analog of what I said for Maxwell theory in this context, which is a little bit different. But notice that there's nothing that's charged under these symmetries in the context that I was talking about, because I was talking about the maximally supersymmetric Yang-Mills theory. Everything was in the adjoint of the gauge group. So this U1 is basically a decoupled field, and even though it has these symmetries, it's really only at the free field level that anything interesting is going on.
I see.
But in a sense, this is what makes these 60 examples more interesting. That you have a version of the story that applies in a rich setting with non-abelian gauge symmetry.
Right.
Okay, another question?
Hi, Thomas. Nice talk. I have a question. So you gave these 2 ways to understand this 2 group. One, in terms of the action of the gauge transformations on the background gauge fields, and the other in the terms of the 2-point function of this current.
Correct.
Is there an easy way to see? Is it obvious that these things should be related?
It takes one intermediate line, perhaps. So the easiest thing to do is to take this equation, which is really an OPE, and I've dropped on the right-hand side a singular factor, which is a typical OPE factor involving the distance between these 2 points. So you should think of this as an OPE with a singular term corresponding to the distance between these 2 currents. Because of the dimensions of the fields involved, that singular factor is such that when you hit this left-hand side with one derivative, so in other words, you take the conservation equation on one of the 2 currents, this singular factor turns into a delta function. So this OPE can be characterized instead by saying that the divergence of J fused with J0 gives something like a delta function, actually a derivative of a delta function, with some index rho contracted into the 2-form current with free indices rho and nu. Okay. So this OPE equivalently can be thought of as a contact term containing the 2-form current operator in the divergence of J hitting J. Now that is easily seen to come from this non-conservation equation, because this non-conservation equation has one divergence of J on the left-hand side. It has the instanton density, which is the same as the 2-form current on the right-hand side. And then it has one more copy of the background field. So in order to get rid of that copy, I take another functional derivative of this equation with respect to this background field. And what that does on the left-hand side is it inserts from the exponential in the path integral another current, and it turns this piece into a derivative of a delta function. So differentiating this equation with respect to the background field A gives you this contact term in the fusion of the divergence of J with J, and that's in 1-to-1 correspondence. You can integrate that up to this OPE. So you see that all these things are equivalent.
Another question?
Can I ask a question?
Go ahead.
Yeah, so if we look at page 15, so for the gauge transformation of B, the 2-form field B, I'm wondering whether the coefficient in the denominator 4 pi is problematic or not.
Why do you think it's problematic?
Because because lambda L 0 is 2 pi periodic quantity, right? So if we
actually everything I've written here, everything I've written here is not abelian, and I haven't told you exactly how I normalized all my generators and so forth. So I can hide behind that. However, a version of your question would be, what is the correct normalization of the terms I wrote in, say, the abelian case?
Yeah.
And in that case, you're absolutely right that the correct normalization, maybe let me write it in a little box here, would involve something like an integer k divided by 2 pi, and then lambda times the abelian f.
Okay.
That, in the abelian case, is, as you, I think, anticipated, the correct normalization, because, this is how this whole thing takes care of itself kind of at a global level. If you do a large U1 gauge transformation, then lambda jumps by 2 pi.
Mm-hmm.
And so this Green-Schwarz term is superficially not invariant under that, because now you're shifting b by kappa over 2 pi times f. Now, kappa over 2 pi times f is exactly the kind of thing that can be absorbed by a one-form gauge transformation of the B field, as long as kappa is an integer. So you see that for all this stuff to work, it's very important that kappa is an integer. So I didn't talk about that, but you could have asked me at some point if kappa is supposed to be something like an anomaly coefficient or not, or if this n is supposed to be an anomaly coefficient. In a sense, the answer is no, because I was kind of presenting this whole story as a modification of the global symmetry. So it's not really an anomaly. But what you see in this context is that these constants are still quantized and they still obey interesting constraints. And they appear a little bit in this two-group story like the structure constants of a Lie algebra would.
Okay, thank you.
Next question. Don't be shy.
Thomas, may I ask something?
Sure.
Yeah, go ahead.
Look, this is a question I don't have completely clear, but let me ask it and feel free to cut me if it doesn't make much sense. Suppose that you were to, let's go back to the example of the 1-1 theory, right? The 6-dimensional 1-1 theory. And suppose that you were to compactify it to 4 dimensions, right?
Yeah.
In a way that would touch their symmetry, so not anymore SU2 cross SU2. Do you think the deformations of the two-group symmetry would have consequences in 4 dimensions?
And
if so, which consequences would you expect there to occur?
I suspect that if you go to the strict 4-dimensional limit, so if you really take the manifold on which you're compactifying to be small and you decouple everything that's massive, it might disappear. And the reason that doesn't have anything to do with the two-group itself, but even with the one-form part of the symmetry that I'm talking about. The one-form symmetry, whether or not it's embedded in a two-group, is the instanton density in 6 dimensions.
Mm-hmm, mm-hmm.
And the instanton density reduced to 4 dimensions does not lead to anything that we ordinarily think of as a global symmetry.
I see.
That being said, there's a small remnant of it. There's a small remnant of it, which has to do with the fact that the instanton density appears as a coupling in the Lagrangian, and the coefficient of that coupling is theta, which is a periodic variable.
Yes.
So there could be some kind of interplay with theta.
Good.
But my first reaction would be that a lot of this decouples when you KK reduce, but I certainly haven't analyzed it in detail.
Good. Thanks very much.
Next question.
Hi, Thomas. That's a very nice talk.
Hi, Sam.
I have 2 vague questions. The first one is if you take the story and you embedded it back into string theory, would you learn something new about brain physics and anomaly cancellation when these background fields become dynamical and everything should cancel? And the second vague question is, if I looked at a gauge gravity dual to some story like this, how would you see the deformed current algebra from the closed string perspective?
Okay, so let me, and both are excellent questions. I have a clear answer to the second one and a vague answer to the first one. So the gravity dual of this story is as naive as you might think it is, which is that, so this story on the boundary side is something that is like a Green-Schwarz mechanism for background fields. And in the gravity dual, all background fields for global symmetries become dynamical. And what this simply becomes is a dynamical bulk theory with an ordinary Green-Schwarz mechanism. Okay, and there are many of those. Okay, so that's one thing. The first question is very interesting, and I don't have anything particularly useful to say to it, about it. One thing that one might worry about when studying, for example, little string theories and their global symmetries is to what extent exactly those global symmetries are good symmetries of the full UV complete little string theory, to what extent you can really couple that theory to background fields and still have it decouple from the bulk. These are a little bit subtle questions that I have basically swept under the rug. I've treated these theories mostly as machines that generate interesting low energy effective field theories and then analyze them in field theory language. But I think it's an interesting question to analyze the way in which the bulk B, so the B field that couples to my two-form current, my instanton current, is the bulk B field. It is the B field of string theory. And in a certain naive sense, it decouples and becomes frozen into this background field when you take the decoupling limit. But the exact way that happens in the full construction is typically a bit subtle, and I don't have any claims about it, but I think it would be interesting to study it from this point of view.
Great, thank you.
Another question? Okay, well, maybe if there are no more questions, okay, it doesn't look like there are. I'll thank Tomas for an excellent seminar, and thank everyone for their questions and for coming to visit us virtually here at USC. And please look out for more seminars. And if you wish to unmute yourself and applaud, or use the applaud symbol to our guest, that would be very nice. So, and without further ado, I'll say goodbye and thank you. And see you next time.
Thanks, everybody.
Thank you.